Our next topic deals with what we call the electromagnetic spectrum, or abbreviated oftentimes as EMS. Electromagnetic waves are, as the name implies, a combination of electric waves or just regular waves and magnetic waves. Now, electric waves and magnetic waves run at right angles of each other. And that's described pretty well by Professor Dave in that video. So if you haven't watched those two videos that I've asked for, one for Professor Dave, the other Mr. Anderson, we'll stop right now and watch the Professor Dave one first, then we'll talk a little bit about what he had, and then we'll talk about what Mr. Anderson had with Amplitude. All right, so go ahead and pause now if you've not seen the video yet. All right, now, when you have high energy systems like stars, and our sun is a star, as you know, there is a series of fusion reactions taking place. Now, fusion reactions are the highest energy reactions that exist. And at the very beginning of the Big Bang situation, where all this intense energy was compacted in one small space, it was too much to contain, blows apart, and then a series of fusion reactions started to take place. And since the vast majority of elements, most likely at that point, was hydrogen and helium, the fusion reactions began to take place at that point. Now, the hydrogen in fusion creates helium, and the helium in fusion produces beryllium, and the reaction of hydrogen and helium in a fusion-like reaction will produce lithium, and it keeps going on and on and on until the cooling down process. As the farther away they get from the heat source, the less likely that more elements are going to be created of heavier masses. And it's an interesting topic, and there's a number of works out there, if you're curious about that, to follow that very idea. They talk about a little bit in a book called The Disappearing Spoon, which I highly advise. But regardless, this is high energy chemistry. And when high energy reactions are taking place, they produce waves. Because of the energy being produced, it's being transmitted in whatever direction. It's going to be in a spherical path, but it's going to create both a longitudinal and a transversal pair of waves as they go out. So, what we are going to be looking at is using the velocity of waves equation that we used before, which is V equals lambda times F, or V equals lambda over period, or T. The thing is, though, when these things get pushed out, they go at the, what is considered the highest velocity possible for any particle, which some people call the speed of light. It's technically the speed of electromagnetic waves. All waves, and light is included as an electromagnetic wave, all waves are traveling at the same speed, which is 3 times 10 to the 8th meters per second. So we call that value C, because in a sense it is a constant. It is not going to waver. There's no, I mean, when light hits air, it will slow down. When light hits water, it will slow down. But when light hits, is in a vacuum, it will not slow down. There's nothing to slow it down at all. So it remains at 3 times 10 to the 8th meters per second. Now, something brought up in Professor Dave's video is the idea of amplitude. And amplitude is basically the size of the disruption. Now remember, all these waves are transmittance of energy. And energy is being somehow condensed into one area, or it produces a wave or whatever. But the higher the frequency of the waves, the stronger the energy is being transmitted. But also involved in that is the amplitude. Now, the amplitude is how high or low from the medium. for a transversal wave, so the distance from the medium to the crest, or from the medium to the trough, that would be considered the amplitude for transverse waves. For the other wave, where you have the wave going along with the medium, but it's going to, when an explosion or a loud noise or any energy transfer is being made, the waves get pushed together, and then that creates a lag after it, and every wave that's created after that is going to be measured by the thickness of how the various waves are scrunched together as it moves along the path there. So that's really important in sound, and there's other areas too, but I just want to make sure you understood what he meant by amplitude and what that might infer. In our next topic, we talk about sound waves, and we'll get into a little bit more of that. So the bottom line here is that electromagnetic waves are going to be looked at in 7 ways, because the higher the frequency, as I said, the greater the energy, which means the lower the wavelength, the greater the energy, because there's an inverse relationship between the two. And when you get in a certain range of frequencies / wavelengths, you get a different kind of wave that is, because of the difference in energy, will actually do different things as a result. We have gamma rays, and nothing but gamma rays, you will have virtually no carbon life, which is what we are, organic life, because it will just burn all the cells. So the moderation of the energy as you go down makes it more likely that we are going to be able to live. Gamma rays is a constant concern for astronauts in space, so they have to wear leaded suits, because the lead in the space suits will actually absorb gamma rays. If they were to go out with just an oxygen mask on, they could die because of the gamma radiation that is constant out in space. So let's look at those 7 areas. Radio waves are the weakest one, and way back when television and radio were a thing, based upon antennas transmitting signals, the signals were transmitted as radio waves. Because they were so weak, they were affected by weather pretty bad. AM radio was more affected than FM because of various modulations involved, but it was an issue. And so it was in the 1990s when they decided to go digital for everything, and that pretty much knocked out any use we have for radio waves. However, one of the ways of identifying objects in space is by looking at the radio waves that are produced from the objects in space, particularly stars. Microwaves is next. It's the next strongest or second weakest of the entire 7. We know that we use this in microwave ovens, but we also use it in radar. We're going to talk about that when dealing with Doppler effect later on. Infrared waves is between 100 micrometers and 700 nanometers, so we're getting stronger as the waves get smaller and smaller. The frequency gets larger and larger. And infrared waves are used in laser metal cutting, heat lamps, and night vision. So the night vision goggles that you may be somewhat familiar with uses infrared waves because it picks up the heat in living bodies that it picks up. Okay? Yes, it picks up stuff they pick up. That's really well put, Mr. Campbell. Thank you very much. Next is the visible light ray. Now this is extremely small, very narrow range. And the weakest of the light is red, and the strongest of the light is violet, which explains why infrared is just short of the strength of visible light, and ultraviolet is just after the visible light strand. So that's the best way to remember which is weak and which is strong. This is going from weakest to strongest. Red light is the weakest of the color lights. Violet lights are the strongest. Okay, ultraviolet waves, now we hear a lot about that. There was a time in which we had issues with the ozone layer of the Earth. The ozone layer was being eroded by freon gas that escaped into the atmosphere, and they found that freon gas was blocking the formation of ozone. Ozone is a very unstable compound, but it helps us be protected from ultraviolet rays because it will absorb the energy of the ultraviolet rays to create the chemical reactions that produces and decomposes both at the same time the ozone. Well, if you lose the ozone, you lose the barrier that we have around the Earth, and a lot of people were getting skin cancer. They have since, and that also, one of the things they found happened with that was that there was a gigantic hole at the poles, and we suspect it's because of magnetism, that the holes were being created in the ozone layer. Rather than directly over us, it would migrate towards the magnetic poles, and the holes were opening up, and then the ultraviolet rays would get through, and people would get skin cancer from that. They have since found that the holes are almost completely gone. There's still a little bit there because there's still some use of freon going on. Ultraviolet is also used in examining plant life and animal life. And that's a biology thing, so ask Ms. Bugos about that. I don't know how it's used. I should, but I don't. X-rays. X-rays we're familiar with because of the X-rays of people's bones. This is a highly dangerous part of the spectrum. We're getting to the really strong stuff. This is the second strongest waves or rays, or whatever you want to call it, in the electromagnetic spectrum. And this is why you have to wear some kind of protection now. It didn't used to be that way. You have to wear protection now to keep from being irradiated with too much radiation, because the problem is that radiation, once you got it, it's really difficult to get rid of it. In fact, it's virtually impossible. So you have to limit the amount of radiation that's being given to you. And the last one is, like I said, gamma rays are the strongest ones. They kill bacteria. It's also used in sanitizing medical instruments. It's very, very, shall we say, toxic or dangerous to living organisms. And bacteria is a living organism, and so it is able to be destroyed by the gamma rays, and therefore we decrease the amount of infections in the medical profession when surgery is going on. All right, a couple of examples here. So let's talk about the examples.